Well, we saved the best to last. The last sequence we discuss is the Fibonacci sequence. This is not only the best sequence, but it's the oldest sequence. Fibonacci was in 1202, and he was interested in the populations of rabbits. And his model for the number of rabbits in a population was as follows. F1, the number in the first week, is equal to 1. F2 is equal to 1. And then after the second week, Fn is equal to Fn minus 1 plus Fn minus 2. And so if we choose n equals 3, then we have F3 is equal to F2 plus F1, which is 1 plus 1, which is 2. N equals 4 gives F4 is F3 plus F2, which is equal to 2 plus 1, which is 3. And you see there's a pattern here. We just add the last two numbers in the sequence to get the new number. So the sequence is 1, 1, 2, 3, and 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21. And so on. Okay, so I'm going to write this up over on the other side. Again, 1, 1, 2, 3, 5, 8, 13, 21, and so on. Now there is a beautiful kind of geometrical interpretation of the Fibonacci sequence. I'm going to start by drawing squares of dimension the same as the Fibonacci numbers. And so I draw the first one, a 1 by 1 square. Right beside it, I do a 1 by 1 square, that's F2. And then the next one is a 2 by 2 square. And then a 3 by 3 square. The next one is 5 by 5. What comes after that? That's 8. So we'll draw up here 8, and then comes 13. Okay, and now we have 21. Okay, it's kind of a cool pattern. If we take the corners here, I draw a little dot on each one that we're interested in here. And if we connect the dots, and there should be a dot there too, we get the Nautilus spiral. So I'll put on the numbers in the sequence 1, 1, 2, 3, 5, 8, 13, and 21. And it can continue. Isn't that beautiful? So you might be asking yourself, how does COVID-19 relate to the Fibonacci sequence? So, interestingly, there is a new model by F.S. Dundar, 2020, that just came out that talks about the connection between COVID-19 and the Fibonacci sequence. And so the model is a little bit different than the one we've been using. We suppose that an infection takes place over several weeks. And that an individual infected in week T infects another individual in week T plus 1, and a second individual in week T plus 2. So this is a little bit different than the model we had because it spreads out the infection over a 2-week period. And we might ask ourselves, what's the total number of infections per week? So we start with an individual in week 1, and they live through week 2 and week 3. In the second week, they produce a new individual, and that individual lives through week 3 and week 4. In week 3, the first and the second individuals both produce new individuals, and they will both live through week 4 and week 5. You can kind of see a pattern here. And then we have 3, 3, 3. And then in week 5, we have individuals that were alive, born in week 3 and in week 4 are producing new individuals. And we'll have a 5, 5, 5. In week 6, we'll see 8 individuals, and they will last the 3 weeks. In week 7, we have 13, 13, and so on. And then in week 8, we see 21. And so if we want to add up the total number of infections, in week 1, we have 1 infection. In week 2, we have 2 infections. Then we have 4. Then we have 1 plus 2 plus 3 is 6. Okay, then we have 10, 16, and 5 plus 8 plus 13 is 26. And in week 8, we have 8 plus 13 plus 21 is 42. Okay, so for the Fibonacci number, we just start with week 2, and 2 is equal to 2 times F2, and 4 is 2 times F3, and 6 is 2 times F4, 10 is 2 times F5, 16 is 2 times F6, 26 is 2 times F7, and 42 is 2 times F8. And just to remind you, F2 is equal to 1, F3 is equal to 2, F4 is equal to 3, F5 is equal to 5, F6 is equal to 8, F7 is equal to 13, and F8 is equal to 21. How cool is that? So the disease progression in this slightly different model actually follows the Fibonacci sequence.